Hello everyone, I just wanted to record a short prelude before the main recording here. I wanted to clarify some things about today's recording. You can see that my screen is blank so far. So basically we recorded lecture 4 part 2 live, and I have the recording, but things went a little bit south during the recording. The main focus of today's lecture was the a theorem on vector bundles and how when a manifold would have a vector bundle. The proof was very long, and we got I got stuck in the middle, and I realized that the proof that I had the explanation for the proof that I had written in my notes was wrong, and so it I think the live explanation became a little bit incomprehensible, and so I opted to instead re-record this section, and instead of recording it all in one go, I thought it would be easier to record it in a few passes and then stitch them together. So that's what you're going to see next. And I also wanted to take this time to there are going to be some parts in this lecture where there's going to be a little bit of background noise. There's like a little bit of construction going on around here, which is pretty loud. And my room is not very well soundproofed. So apologies, you're not going crazy. There are construction noises going on in the video recording. And number two, in a previous time, we were trying to I wanted to redo a specific calculation that we failed to do last time on the live recording, when we were looking at V star O cross C, and we were trying to we had this element of it called phi. We wanted to decompose it in terms of phi equals to phi 1 plus phi 2, where this was an element of VC star, and this was an element of VC bar star. But we had to prove that this was from VC star and this was from VC bar star, and so that meant that J star of phi 1 is equal to plus I phi 1. I'm going to do one of these. We got stuck in, I wanted to try to do the algebra live, and I got stuck on one of the steps, but I wanted to show everyone how to do it. It's J star of phi 1 expanded in terms of its definition, which was actually half phi plus J star, minus I over 2, if I'm remembering correctly, J star of phi. J star is a linear map, so we can distribute it all over. So we get this. But notice that J star, since it's a complex structure, this is minus 1, and so half J star of phi minus I by 2. Now it'll be plus I by 2 phi. And this is the key step where I got stuck. So here I was trying to I got railroaded into I got tunnel visioned into trying to figure out what J star of phi was, but J star of phi doesn't have any extra decomposition. What we really need to do is we need to take plus I out of factor it out of this expression. If we put this first, then we get something that looks like this, half phi, and then the plus I leaves a minus I over on this term, because 1 is equal to plus I times minus I. So we get this. But notice what that is. That is, if I were to highlight it in a different color, that is exactly what we started out with, which is the definition of phi 1. So that results in plus I phi 1. And therefore, J star of phi 1 is equal to plus I phi 1. J star of phi 2 is very similar. And we're not going to do it. I'm just going to highlight that in that case, we would just have a plus here instead of a minus, and we would take minus I out of here instead of a plus I, and that would give us this thing, minus I phi 2. And that would prove that phi 1 is an element of VC star, and that phi 2 is an element of VC star bar. All right, so I hope that clarifies what that part of the working. I'm sure some people have already figured out this, but I wanted to have it be part of at least one of the recordings. So I'm gonna give it over to President Saif to start the main lecture. So goodbye, everybody. Hello, everyone. Welcome back to Complex Differential Geometry, where we were in the middle of lecture 4 last time, and we would like to define these things called vector bundles. And we did that last time, and so let's recap what we did. First thing we did was we defined this thing called a vector bundle. Very briefly, it was a triple EM pi, where we had this M was this base manifold with something protruding out of it, which was the bundle space. It was diffeomorphic. This thing is diffeomorphic to M cross F, where F is this fiber, and we'll call it FP to signify that it's the fiber over P. And so this space, yeah, let me clarify that this is diffeomorphic. Diffeomorphic to M cross F, not M cross F itself. So this is E, and lastly, pi is a map that maps points on this fiber FP back to P. That's what we had last time. And so the second thing is that we made the before we go to the second thing, so and the last thing that we needed on this was a set of linear transformations G alpha beta of P, or G alpha beta, sorry, I'll clarify that in a bit. So an alpha beta comes from some index set, call it A, and so these were of this nature. So these are maps that go from U alpha intersection U beta, and they go to GL of F, where F is this thing called the fiber. And so these are called transition maps, but they're different from the chart transition maps. They transition between the representations of FP on U alpha to FP on U beta. For, when we call it alpha beta, that's what we're saying. FP on U alpha to FP on U beta. So what this is saying is that if you, for a given P, I will give you a linear map. That linear map we will call G alpha beta of P. And this is a linear map on F. So this is going to act on vectors in F. If this is holomorphic, then we get something called a holomorphic vector bundle. And so the next thing that we defined was this thing called a global section. A global section is a map S that goes from M to E. It tells you it's literally a cross section of our manifold, of our vector bundle on the manifold. And what it does is that it tells you, okay, well, I intersect this fiber at this point, and that gives me a choice of a vector V element of FP. And it does this for every fiber over the entirety of this space, giving us a vector for every point on the manifold. And so this is the differential geometric version of a vector field. So this is a vector field on M. And this is subject to the constraint that pi after S must be equal to the identity map from M to M, which means that if so the way you can think about this is that if I have this M and there's this fiber, then S should map. So we're saying that this is P, and so S is a map that must map somewhere here on the same fiber. So this is S. So then let me mark the endpoint in red. So then such that pi can map us back to its base point and complete the loop. So this would give us the identity, right? Because we ended up back where we started. So this ends up giving us the identity as required here. So this condition restricts us to only allowing S to map a point in M to its own fiber. So this is the to its own fiber constraint. Then we looked at local sections, which are the same idea as sections, which are continuous surfaces. In the bundle, but instead of being over all of M, they're over a open subset of M. Let's say U alpha. If I have the bundle, the part of the bundle, which I call the restricted bundle, or you could say the bundle restricted to U alpha. Let's not draw the fibers. It'll be clearer. So if we have a section on this, then this is called a local section because it's a section over a local neighborhood. And on a vector bundle, you can patch up all of these local sections to make a global section. Right. So then we took a set of these local sections, L, where let's call them S alpha, where alpha is an index. So each of these S alphas is a local section. S alpha is a local section over U alpha, where alpha is an index that's going to run from 1 to Q, where Q is the dimension of the vector space F, of the fiber. So what does the local section tell us? Well, in brief, the local frame field. These are called local frame fields. Local frame fields. So these are sets of local sections. So each local section gives us a choice of a vector for every point above U alpha, on U alpha. And so what this does is it extends the concept of a basis on a point P. Well, at a point P, there is, let's say, a vector space like TPM. So I could have a basis for TPM. If I collected the basis for TPM and the basis here, let's say that there's a point Q. So we collect the basis for TQM. And we collected all of them, every point in U alpha. We aggregated all of the bases. And we could choose a basis using a section, or we could choose a basis vector for every point using a section, and with enough local sections, so Q of them, we would need Q local sections. Each local section chooses one of the basis vectors for every point in U alpha. So then Q local sections will choose Q basis vectors for every point in U alpha, which means that local frame field is kind of an extension of the concept of a basis to a local neighborhood. And we, in looking at local frame fields, we looked at this specific example called the tetrad formalism, which is a local frame field for curved spacetime. So that's what we did last time. So this time, what we're going to do is we're going to start off with a result that is going to be very important. We're going to talk about a theorem. It's going to be a really long winded. We're going to try to prove this theorem, and it's going to be a long proof. So hopefully you guys will bear with me while I try to prove this. This is condition. I don't know if there's a neater name for this theorem, but this is what I'm calling it. Conditions on or what did I name it? Conditions ensuring a manifold has a vector bundle or admits a vector bundle. So the claim of this theorem is that given that we have a manifold with a certain set of conditions, we are guaranteed to be able to construct a vector bundle on it. Okay, or we are guaranteed to have a vector bundle on it, and we're going to show that we do by construction. Okay, so let's look at the statement of this theorem. So first things first, M is our m-dimensional smooth manifold. And let's consider a open covering U alpha. Alpha is an element of some index set A. So this is an open covering of M. Open covering of M. We're guaranteed to have an open covering of M because we know that M is a manifold, and we can take it from a topological manifold, and we can take it from the topology. So, but we can also take it from the chart. And lastly, so bullet points, third bullet point, F is a q-dimensional vector space. These are our ingredients. So now let's look at the conditions. Conditions. One. Okay, so first of all, alpha and beta are both elements of this index set A, such that U alpha, U intersect with U beta is not empty, meaning that U alpha and U beta intersect with each other. And so the first condition is that G alpha beta such U alpha intersect U beta to GL F exists, and maybe I should put that and over here, and is smooth. Number 2. So this is a further refinement of the previous one. So G alpha beta satisfies one if both of the indices are the same. So if beta is equal to alpha, G alpha alpha at P, remember when we take it on P, we're restricting it from being this collection of linear maps over all of U alpha intersect U beta to a single linear map associated with P. And this has to be equal to the identity. which kind of makes sense, you know. If I want to take the transformation from of alpha, sorry, if I'm trying to take the transformation of like fp as it is on u alpha to fp as it is on u alpha, where like I would say u beta, but instead I'm saying u alpha, then I would expect that to be the identity map, right? If I go from u alpha's representation to u alpha's representation, then it should be the identity map. That's what this condition is saying. And number two is that if p is an element of u alpha intersection u beta, then and intersect another one, u gamma, and this intersection is not empty, then g alpha beta after of p, again, after g beta gamma of p, so all at the same point, is equal to g alpha gamma of p. So some sort of chaining property. So that if I go from one vector space to the vector space indexed by alpha to the vector space indexed by beta, and then I go from the vector space indexed by beta to the one by gamma, then it's the same thing as using the linear transformation that goes straight from alpha to gamma. That also seems to make sense. So if these conditions are met, so number 1, number 2, and 2 sub meaning 2 sub 1 and 2 sub 2, then we are guaranteed. So let's say if, then we are guaranteed that M admits a vector bundle EM pi with transition functions g alpha beta, where alpha and beta are from our index set, and f, the typical will be the typical fiber. I mean, I missed the idea that this is, so this here I would say are the transition functions, or being, I suppose grammatically, being the transition functions, transition maps, and f being the typical fiber. So yeah, so that's the statement of the theorem, is that if we satisfy all of these conditions, then we're guaranteed to have this vector bundle. So what we're going to do is we're going to prove this. So I'm going to try my best to explain this proof. It's very lengthy. It has a lot of parts. So we're going to go at it part by part. But you can look at, I would like to say a more thorough version of the proof, but actually a more terse version of the proof is found in Steenrod 1957. I think the book is called The Topology of Fiber Bundles. It's on page 17. Sorry, page 14. Yes, page 14 to 15. The end of it is on 15. Steenrod doesn't explain everything about this proof, so I've filled in a lot of the blanks. But let's get into it. But right before we get into it, there is one important thing to say, which is I want to remind everyone what a continuous function is. Continuous function. A continuous function, let's say that f going from a to b, where a is the domain and b is the codomain, is continuous. That implies that if u subset of b is open in b, then f inverse of u subset of a is open in a. That's what it means for a function to be continuous. Now, a full explanation of why that's the definition of a continuous function you can find in Munkres, as we've been using as our reference for topology. Munkres talks about why this is the definition, and if you want more explanation of all of this, what you can do with continuous functions and so forth, you can do that, but you can look into that. But for our purposes, we just need to know this, because this definition will be implicitly used over and over again in the proof, because we're going to be using M as a topological manifold, and we're going to be constructing a few more topological manifolds off of that. So this is going to be pretty useful, and we're going to need to prove that some of the functions are continuous. Okay, so let's start the first part of the proof. Let's go to the next page. Let's start the first part of the proof. The first thing that we're going to do is we're going to turn A, our index set, into a topological space. Topological space. In order to do that, remember, we need to give it a topology. We're going to give it the discrete topology. The discrete topology is where we take the power set of that set, and so the power set is the set of all subsets, and we say that every element of this set is an open set. Every element. So every subset, let me just cut to the chase and say, so every subset of A is an open set. I think the reason why it's called the discrete topology is because topologies in some sense allow you to distinguish points from each other, and so the discrete topology is the topology where you can distinguish the most amount of the manifold from, or most amount of the topological space, from each other, as opposed to, let's say, on the other end, where you have the indiscrete topology, which only has the set and the empty set, the whole set and the empty set, where you can only distinguish between those two sets. So in the topology. Okay, so now that we've made a topological space, we can now look at this set M cross F cross A, and remember this, we called this the local trivialization. And you can think of this as just adding on some information about which local patch or local neighborhood we are looking at that trivialization from. This is going to become relevant because we're going to have multiple local patches by which to look at the local trivialization from. So we said that, okay, well, think about the manifold as being diffeomorphic to this product, right? M cross F over the entire manifold. And so it's not isomorphic to M cross F, but it is uh, diffeomorphic, but local patches of the vector bundle will be yeah. So because this is what we're doing to in order to construct the vector bundle. So this has something to do with the vector bundle, and what we're saying is that we're going to construct something that looks like the vector bundle on the local patches, and then we're going to patch them all together. So let's take T to be a subset of M cross F cross A. So where, by the way, this is the Cartesian product. Cartesian product. So we want to say that T is a topological space. So before we do that, actually, the elements of T look like this, right? So you got, first of all, you have that elements of M look like this. They're points on the manifold. Elements of F are vectors. And then elements of A are indices. So we have a triple. We have a point on the manifold, a vector, and an index. Those are the structure of the elements of T. So T, we can make T a topological space. We need two things. First of all, we need the product topology. Product topology on M times F times A. So remember what we needed to for turning A into a topological space. We needed to give it a topology, right? So which means that we needed to define what are the open sets on A, and in order to figure out what are the open sets on M cross F cross A, we could just say, okay, well, we already know that M is a topological manifold, and so it's a topological space, and so M has open sets defined on it. So let's just say, take whatever an open set is on M, and then take let's say that F has, at least it has the indiscrete topology, right? So at least F, whatever the topology, actually we don't need to worry about whether this is indiscrete. Whatever the topology is, by definition, F is going to be in the topology. So let's say that F is a topological space, and so F must be in that topology, and then we can just take the singleton set of some of alpha, where this alpha connects to this alpha. Right, that connection reminds me that this P, we are required that this P is an element of this U alpha. That's a requirement for this point. When we index it with this alpha, that means that this P comes from this set U alpha. Okay. So, okay. And because A, coming back to what we were talking about, because A has the discrete topology, every subset of A is an open set, right? So we know that this is an open set on A. So with the product topology, in the product space, we're going to say that any open set is if all of these are open sets, then we get an open set in T. So now that we've defined, open set in this set, we actually don't have T yet, because T is a subset of this set. Okay, so then we need, why did I number this number 2? That's strange. So yeah, so that was number 1. Number 2 is we need the subspace topology. Subspace topology. The way we construct a subspace topology is exactly what it sounds like. If T is a subset of the original topological space, then we can construct the open sets on, or we can define the open sets in a consistent way on a subset by saying that T intersection U is open in T if U is open in, we call it the ambient topology. or you could call it the parent topology. Ambient. That's supposed to be an M, by the way. Ambient topology. In this case, there would be the topology on M cross F cross A, right? So now, okay, cool. We have defined what the open sets on T are. So that means that T is now a topological space. T is a topological space. We called it T because it's a topological space. Okay. So the next thing that we have to do is we're going to remove some of the points from T. So remember how we were talking about the fact that we were going to patch these local patches together. The idea is that let's say that we have this point U alpha. So we have U alpha cross F, right? We were calling this the local trivialization. Well, in fact, the local trivialization would be something like U alpha cross F. That would be a local trivialization. And so so that would correspond to having the fibers jutting out from here. But notice that if we have an intersecting open set, let's call that U beta, and let's think about U beta cross F. I'm going to put that in a different color. Maybe it'll stick out. What's the problem? There's this overlapping region, right? Where we have both fibers from U alpha cross F and fibers from U beta cross F. But in a vector bundle, we don't have two fibers at the same point. So we're going to have to do something called deduplication. Deduplication. And when we try to deduplicate something, and what we've done so far is we use an equivalence relation. And as per the usual convention, we're going to call this equivalence relation tilde because we don't have any other equivalence relations, so it's fine to use that. So we're going to say define tilde, or tilde, whichever way you like to pronounce it. I'm going to pronounce it tilde. So define tilde so that well, we have to say what it's on. Define tilde on T such that P V alpha, a point on T, is tilde related to P prime V prime beta if P is equal to P prime. So P and P prime are the same point on M, and V is equal to, let me make sure that this is correct. Yes. Oh, let me write this the other way. G alpha beta P dot V is equal to V prime. So V and V prime are related by a linear transformation. So the bundled, the fibers on the two bundles, so let's say the green version of FP and the red version of FP don't have to be the same vector space. They just have to be vector spaces that are connected by a linear transformation, and that linear transformation is G alpha beta of P. So we're guaranteed that this alpha beta exists because that's part of the conditions, right? Condition number one. Let's go back down to the previous page to see that. Let me see. Yeah. So yeah, we know that this exists, right? So that's why we can use this definition, and it's all well and good. So let's go back up. Okay. So we've defined tilde. So let's define a space E, which we're going to say is T modulo the equivalence relation tilde. What does that do? Well, we've seen that what tilde removes are duplicate versions of the fiber, right? If there are two fibers in two different local patches, local trivializations, then they get turned into one single point, right? So if we had two of these, then basically we would have something like P, V, alpha, and we would have P, well, remember, they're supposed to be the same points, so G alpha beta of P, V, beta, right? So these points are actually the same point, and this creates an equivalence class P, V, alpha. We only have to count them once. We don't have to count the separate FPs twice. So what we're going to do is we're going to talk about, we're going to define this map. We're going to define this map Q. Oh, before we define this map, let me just say something. We called it E, right? E will be our bundle space. So what we're doing systematically, I forgot to say this at the top, but what we're doing systematically is we're trying to show that given these conditions, that we can construct a vector bundle, right? So what we're doing is one by one, we're going to construct E, we're going to construct pi, and then we're going to construct G alpha, the set of G alpha beta, and we're going to show that we have all of the ingredients necessary to make a consistent vector bundle. And that's what is going to tell us that for given these conditions, that we always will get a vector bundle. Okay, so this is our bundle space. This is what's going to end up being our bundle space. It is this subset of M cross F cross A, which is deduplicated, right? We've deduplicated the points on it. So E is T with redundant fibers removed. This is something that took me a little while to understand, but when we say that T is a subset of M cross F cross A, I think what they mean, what Steenrod means in the proof, is not that it's a subset of M, that it takes the subset of F and A, and so it takes a subset of this space of possible points. It doesn't fill up M cross F cross A, right? But it doesn't skip on any part of M, because we do need all of M in order to make the vector bundle. At least a vector bundle in the global sense, we would need M to be all of M to be represented. So on M, we have all of these open sets. I'm going to draw them like circles. Right? Yeah. Let me just quickly make the point that all of these together cover M. So this rectangle is what's supposed to represent M. And so let's say that we zero in on one of these. Let's call that U alpha. So far, what we have is that there might be another set U beta, where we had those redundant points, right? So in all of these intersections, we're basically attaching all of these fibers, right? We've attached all these fibers. That's where this came from. And where we realize that if we attach the fibers to each of the points, each of the local patches U alpha cross F, then we end up with too many fibers, right? If U alpha and U beta intersect, then you get fibers that overlap each other or get attached to the same point. And so we remove these red regions, and we create one single copy of them. So let me zoom into maybe 2 of these or 3 of these. So let's say that we have this Venn diagram looking situation here. So you have U alpha, U beta, U gamma, and let's color code those. So you have this red region with the red fibers. you have this green region with the green fibers, and you have this yellow region with the yellow fibers. And what we're doing is we're deduplicating these points using this tilde equivalence relation, and then that makes us end up with a shape that looks like this. This is a subset. See, this is going to happen all over M, but it will essentially do something like that. So this is a subset of E, and this is a subset of T. I hope that makes sense. So we've deduplicated the points. Each fiber only appears once for every point on the manifold, whereas here you can see that there's a red fiber and there's a yellow fiber. Here there's a red fiber and a green fiber, and here there's red plus yellow, red plus green, and here we have a green and a yellow fiber. So we have duplication, and in the middle you have all three, right? So that's what we've done in this part of the proof so far. And now we will move on to the second part, where we define this function q t to e, which is a function that will take this triple p v alpha, and it will output its equivalence class p v alpha. This is called the deduplication function, or I'm calling it the deduplication function because that seems to be what it does. It sends all of the points PV alpha for each alpha that for each U alpha for each local patch on which that point lies, and it sends it to the same equivalence class, meaning which are elements of E, and those are the deduplicated points. These are points on E. So we can define Q to be a continuous function because E, remember, doesn't have a topology yet. So we just say that if U is an element of E, it's open if Q inverse of U is open in T. This is a definition, and this definition means that Q for this topology is a continuous function, because the pre-images being these things, the pre-images of U, or the open sets, are definitionally open whenever U is open. So Q is a continuous function. So far we've talked about E, which is our bundle space, and the next thing that we want to talk about is pi. Pi is going to be our let's define a map pi which goes from E to M such that pi of this equivalence class representative PV alpha is equal to P. And that makes sense, right? Because PV alpha is the point in E. This is an element of E. And we're saying that we're mapping it to its base point P. And we know which base point it has because it contains that information here. The next thing that we want to do is we want to prove that pi is a continuous function. So let's do that. Pi is continuous. So first of all, let's say that W is open in, let W is open in M. So just W is a set, and we're just thinking of W as being an open set in M. So we need to show, want to show that pi inverse of W is open in E, right? Because pi is a function that goes from E to M. So its domain is in E. So we note that we can see that we're going to use this very specific strategy here, and we're going to show that this thing Q inverse of pi inverse of W is open in T. And we're going to use that to prove this statement. Remember that Q is the deduplication function. It takes points in T and then maps them to the same point in E if they're on the same point in the manifold. So the Q inverse function takes points in E that have already been deduplicated and reduplicates them. That's what I call it. Reduplicate. Or I suppose you could just call it the duplication function. It reintroduces that redundancy into the space E and turns it back into T. So what can we say about this set? Well, we know that T has the subspace topology, so we have to show that Q inverse of pi inverse of W is open in the subspace topology. So let's show that this actually is an open set in the subspace topology. So then we need to show that it's T intersection U, where U is open in M cross F cross A, right? So let's see. Consider this set, T intersection W cross F cross A. Well, W is open. We already said that by definition. F is open, whatever, because it's the whole space, so it must be open in any topology of F. And similarly, A is the whole space, so it must also be open in any topology. And we've chosen the discrete topology, and obviously the whole set is in that topology as well. And in the product topology, this is open. Open in product topology. And so this is an open set. So then it satisfies the idea that it's a U where U is open in M cross F cross A. And the intersection of this with T means that, well, we're not really saying that W okay, so what do I really mean here? What is this intersection refining is what I'm asking here. Is that when we intersect this set with T, what are we losing? Well, we're not using W because as we argued earlier, T has all of W. T has all of M in it. T is still a subset, right, of M cross F cross A, but we argued that T must contain all of M and T must contain all of F for each point in M. So really, what we're saying is that in this space, in this subspace W, in this subset W, we might only have a subset of A. We might have a subset of the indices. Subset. So these are the indices, and W might only contain subset of the indices, or subset of the local patches is a more appropriate way to say it, right? And so a subset of the indices. But notice what is this set Q inverse of pi inverse of W? If this is M and this is W, then pi inverse of w, so pi of some point in E will give us its base point. So pi inverse will, given a base point, give us back the whole fiber, because the whole fiber would have mapped to that base point. So it will do that for every point in W, which will give us this shape here. It's the fibers restricted to W. Fibers, or sorry, I was calling this the bundle restricted to W. Right? So this is pi inverse, also called pi inverse of W, but this is on E, right? This is in E. If we reduplicate the points inside this region so that we get back all of the local patches, so let's say that this part was from U alpha, this part was from U beta, and so forth, and we covered the whole thing. So then there's this subset, right, where there might be overlap between the U alphas and the U betas. Let me color that intersection. So this would be that intersection, U alpha intersection U beta, and here we would have more than one fiber, and we're reintroducing that redundancy in the fibers, and that's exactly what Q inverse of pi inverse of W is. So if that's what that is, then that's exactly what this is. Q inverse of pi inverse of W is equal to this, because this is in fact W cross F, right? And then when we reduplicate it, that becomes W cross F cross A, but intersected with only the indices. So let me write it like this. So intersected with only those indices alpha, beta, gamma, dot dot dot, that are in A, in W, right? So only those indices that are represented inside W, inside these sets that I just drew here, those are the ones that will intersect. But this is the same thing as saying W cross F cross A intersect T, because T, the only thing difference between T and this set here is that it's a refinement on A, which means that these are actually the same, which means that if this is open, then that means that this is open. But remember that what we did last time, or what we did in the previous page, I mean, we defined that if Q inverse of a set is open in T, then that means that the set is open in E. What that means for us is that we've just shown that Q inverse of pi inverse of W is open in T, which implies that pi inverse of W, the set inside here, must then be open in E. But if this is an implication that started from the fact that W is open in M, which means that after a big long chain, that W is open in M implies that pi inverse of W is open in E, which implies that pi is a continuous function. So we've proven this result. So let's move on to the next part. Let me see what's going on here. The next thing that before we do the next thing, let's recap what we have so far. We have E, which is the bundle space. we have M. We already had it. This is the manifold. This is the base space. And we have pi, which is the bundle projection map. The last thing that we need is a set of linear maps. Alpha, beta is an element of A. So we're going to set these up. And much in the same way that we set up the chart transition maps, we said that, well, I called them phi, alpha, beta. So let's use that idea. They were equal to, up to a convention, phi alpha inverse after phi beta. Something like that. So we're going to construct these maps here. So let's start with that. So let's define a map phi alpha, which is going to be taking 2 points P and V, and it's going to be defined using that function that we defined earlier, the deduplication function, P, V, alpha. That's going to be it. So phi alpha is a map that goes from U alpha cross F, because we know that because of the way that Q is defined, that these two are related, remember? So P is an element of U alpha by necessity. And it maps to E, right? But then, if we think about it, we know that pi after Q of P, V, alpha is equal to P. But that implies, since we've defined phi alpha in terms of Q, that pi after phi alpha of PV is equal to P. But what does that mean? That means that remember, this is very similar to what we had before. Pi after S is equal to the identity map. It's a very similar argument where we have this manifold where phi alpha is acting in such a way that it makes a round trip on this fiber. So if this is the fiber, then phi is kind of going from this base point P up somewhere here, and then it's going back down using pi. So this is pi, this is phi alpha. So we know that pi stays on the fibers. So if pi stays on the fibers, then in fact, instead of being E, we can refine this. Let me make that eraser smaller. Pi inverse of U alpha. That's where we're in, because we started with U alpha, and if we're mapping every P back to P, then that means we stay inside that U alpha. That's what it's saying. So we're somewhere inside U alpha. This is a subset of E. So then, so one of the conditions is that G alpha beta has to be continuous. I don't know if that was explicit before. I don't remember if we mentioned that. But G alpha beta has to be a set of continuous maps. So we're going to have to show that phi alpha. So if this is what is going to be our stand-in for phi alpha for G alpha beta, then this is going to have to be continuous, which means this is going to have to be continuous, and this is going to have to be continuous. But we get this one for free. We know that Q is continuous, and then if we restrict it to a smaller domain, it doesn't lose its continuity. So it inherits continuity from Q. If Q is continuous, that implies that phi alpha is continuous. So the next thing that we're going to prove is that phi alpha is surjective, which means that it maps to some part of its domain maps to every part of the codomain, which means that it maps to every part of pi inverse of U alpha. the way we do that is, like, let's say that we have a function f a to b. We can visualize this as this being the set A, this being the set B. A surjective function, this is just revision, will map to the whole of B, right? But that means that if we have any point B here, that we should be able to find a point A there. That's going to be our test for surjectivity. So let's say that we have a point B is equal to PV beta. I'm going to explain exactly what we're doing in a little bit. If this is PV beta, then what can we say about that? What we can say is, oh, well, we'll say that this is inside, this is an element of U alpha. Or sorry, this is an element of pi inverse of U alpha, right? It's any generic element of pi inverse of U alpha. It's PV beta because in pi inverse of U alpha, this is an important idea, on E, let's say, think about the space E. This is the space T, but with the points deduplicated, right? But when we deduplicate, where you might think, okay, but well, wouldn't then this index be alpha because we're inside U alpha? But no, we might have picked a different representative, right? We might have picked the representative from U beta to be the deduplicated point. So we have to show that we have something in U alpha cross F that is going to map to this PV beta, right? So that's what we're going to show here. And we know intuitively that this must be true, right? Because every point in U alpha at least has a point in from U alpha, even if it's overlapping with other open sets U beta, U gamma, U delta. It at least has one point. Every equivalence class will at least have the point from U alpha. Okay, so let's prove that that's true, and that will prove that it's surjective. So, right, first thing is, let's say that okay, well, B must be an element of U alpha intersect U beta. We already said that. But then notice that, and let's take the representative element, right? PV beta. This is not the equivalence class, this is just the element. But we know that this is related to PG alpha beta V. Sorry, we need to take this at P and then V on alpha, right? This is the same point in alpha's local coordinates. And so if we know that this is true by definition because this is the way we defined the equivalence relation, right? P equals to P, V prime is equal to G alpha beta of P V, right? So that we just substituted those things here. So we know by definition this equivalence relation is true. But if this equivalence relation is true, then Q of P V beta. Okay, let's start from the beginning of the chain. B is equal to PV beta, right? Which is equal to the deduplication of PV beta, which is equal to, from here we know, is equal to Q of P G alpha beta of P dot V alpha. Because these are equivalent points, right? So the deduplication function deduplicates equivalent points, but if these are equivalent points, then this will map to the same. The output of these two functions will be the same. It's mapping to the same point. But think about what this is. We defined phi alpha in terms of Q, right? So this is equal to phi alpha of P G alpha beta of P dot V. So we know that for all B element of pi inverse U alpha, this is true. So therefore, this is showing that it's surjective. I hope that makes sense. So the whole thing with the beta and the alpha is that what if our representative was from a different local coordinate, right? What if it was from U beta, where beta is an index that's different from alpha? What we're showing here is that even if that was true, even if our representative wasn't from U alpha, we still could transform it into something that's from u alpha. That's what this is. This is that point that we said that, well, at least there should be a point from u alpha. This is the point. This is that point. So that's what we're saying. So that means that for every point B that we could have chosen, we have a point that will map to that point. So therefore, phi alpha is surjective. So before we continue, I think it's a good idea to kind of get a lay of why, get an idea of why we're doing this. So we wanted phi alpha to be continuous, right? We wanted phi alpha to be continuous, but we also wanted phi alpha inverse to be continuous. So in order to prove that phi alpha inverse even exists in the first place, we need phi alpha to be bijective. So that's the next thing that we're going to do. Phi alpha is bijective. That's the next thing we're going to prove. Okay. So in order to prove that it's bijective, since we already know that it's surjective, it maps to all the points in the codomain, we just need to prove that it's injective, meaning that each point that is being mapped to has only one point in that is being mapped from. So we avoid, so this would be not an injective function. This would be not an injective function, and this would be an injective function. That's what we're trying to prove. Each output only has one input. This is injective. And if it's injective and it's surjective, then it's bijective. Okay. So let's start. We'll show that if, let's say that we have PV alpha, right? And this is an input for our function. Well, this is a point that we could turn into an input. I mean, phi alpha is going to have only the PV part, but let's keep this. And let's say that there are two. So let's say that we have another point, P prime, V prime, beta. So then, oh, sorry, alpha. We want to be in the same coordinate chart. So let's say we have 2 points, right? So then for them to map to the same point, they definitely have to be at the same point on the manifold, right? That's what we said, is that the deduplication function only coalesces and aggregates the same points on the manifold. So we already know that P has to equal P prime. So then what does that mean? So then they have to be equivalent, right? If they're equivalent, then also V is equal to G alpha beta, but yeah, so we would usually put beta, but beta is also equal to alpha. So actually it's G alpha alpha of P V, right? But what did we say about the conditions? Remember what the conditions were. G alpha alpha is actually equal to the identity map. So this means that this is equal to the identity into V, right? Which is equal to V, which means that P prime V prime alpha is actually equal to P V alpha. And there we go. So if we need what we were originally considering 2 distinct points to map to the same point, then actually they would have to be the same point. So only one point maps to a unique output. Let me reiterate. So we had 2 points that we assumed that they were in the same coordinate chart, and we said that, okay, well, just think of them as 2 different inputs to phi, right? We had phi alpha of PV, and we have phi alpha of P prime V prime. And we said, what if they're equal to each other, right? If they're equal to each other, then that means that they're equivalent. And if they're equivalent, then P has to equal P prime, and V has to equal G alpha alpha of V, which means that V is equal to V prime. So then at the end you just get that there's only one point, and so there's only one input for each output. So therefore, phi alpha is injective. So if phi alpha is injective plus surjective, that means that phi alpha is bijective. So that is the result that we're looking for. So that's good because that means that phi alpha exists, or phi alpha inverse exists. Because then the last thing we want to do is we want to prove that phi alpha inverse is continuous. Remember, the reason why we're doing this is that we want to prove that G alpha beta is the transition map. And in order to do that, we need to prove that it's in the form phi alpha p inverse after phi beta p. And we're going to define these functions in a little bit, but we're going to construct them out of these. And so, therefore, we need these to be continuous because we know by definition this is continuous. So the composition of, it must be a composition of continuous functions. Okay, so for it to be well defined. Okay, so this is going to be the largest and most involved subproof. So hopefully I can make a good give a good explanation of this. So we want to prove that phi alpha inverse is continuous. Well, what does that mean? So first of all, let's say show what phi alpha maps. Phi alpha maps u alpha cross f to pi inverse of u alpha. So if we want to look at pi alpha inverse, we'd probably want to reverse that arrow, right? And so now the open for it to be continuous, what we really need to say is that if w is open in u alpha cross f, then phi alpha inverse of w is open in pi inverse of u alpha. But phi alpha inverse is just phi alpha of, so this is phi alpha of w. So what we really want to show is that phi alpha of w is open in E. But remember what the definition of open sets in E was, right? You can scroll back to that part of the video. So this means that Q inverse of phi alpha of W is definitionally open in T. So these are equivalent. That's what I'm trying to say. So we can equivalently show that this is true. And this is going to be easier to do. So that's what we're going to do. So in order to prove that this is true, we're going to need to provide a pretty subtle argument. So let's try to construct it. Firstly, let's construct this set u beta cross f cross beta, and we construct a set of these sets for all beta in A, right? So this is an open, I'm going to say that this is an open cover of M cross F cross A, which is this product set. The reason I can say that is because, first of all, they're all open. These are from the coordinate charts, right? So these are all open sets in M. This is from that u beta. Beta is element of A. So these are all open. We get every beta in A, and we know that these singleton sets are open, right? And F obviously covers F. So and is also open in any topology on F. So this is an open cover of M cross F cross A. So we know that this is a set in T, right? And since T has a subspace topology, we know that as long as we can show that the intersection of this Q inverse of phi alpha of W intersects with one of these sets. Let's call this B beta, and so that intersection with B beta is open. Will suffice, because because this is an open cover, that means that it covers the manifold. So whatever W is, as long as it is inside M, right? As long as W is inside M, which we know is true, this open cover will map over all of W. So, and then if we take the union of all of those, so if we take the union of all of these, then we get back all of Q inverse of phi alpha of W. But if all of those are open sets, if all of the elements being unioned are open sets, then the union of them, the arbitrary union of open sets, is an open set. So therefore, this would be an open set. So all we need to do is we need to show that the element-wise intersection of these is an open set. So that's what we're going to do. But we know that this intersection is contained inside. So let's think about Q inverse. Yeah, so let's think about Q inverse of phi alpha of W. So then if we can think of that as a function from U alpha cross F, right, to phi alpha would map to pi inverse of U alpha, and then Q inverse would map that to T, right? So if we think about that, the domain is in U alpha, right? And so we end up in the part of T inside U alpha. So the part of M that we care about is inside U alpha. But we took B beta, which is equal to U beta cross F cross beta. So this is the set that we are, this is the open set in M cross F cross A that we are trying to intersect with. So therefore the point, any point that we care about must be, P must be an element of U alpha intersection U beta, if we are to be using it. So this intersection that we care about has to exist within U alpha intersection U beta cross F cross beta. Okay, let me reiterate it or say it in a different way, because this is a confusing point, I think. In order for phi alpha of W to work, it must be in U alpha. But in order for us to care about the intersection with B beta, it must be in U beta. So it has to be in both U alpha and in U beta, which means that it must be in the intersection of U alpha and U beta. So, and then if we care about more sets, right? If we have like a B gamma, remember that if we intersect more sets, then this set just gets smaller. Any intersection of this set will be at least equal or smaller than this set. So what we're going to say is that whatever this intersection is of this with that, then this must be at least contained in this set. Contained in this set. So let's call this B alpha beta, where the two indices, we can put a little tilde on it to make it unique. So B alpha beta, this is the set that we need to be restricted to. So let's take this Q function that we're using. We're taking the Q inverse here, and we're restricted to B tilde alpha beta, right? So if we restrict this to B tilde alpha beta, then we can conceptualize this as Q after R. where R is some restriction function. R's only job is to restrict Q to an appropriate domain, which is this set, right? And so this is also equivalent to saying that okay, so let's think about the way that scratch that. Let's think about the way that this map is going to map domains, right? So it's going to go from U alpha intersection U beta cross F cross beta. That's its domain, and then R is going to map that to a restriction of it, U alpha cross F. We don't need to have the alpha because that's a single point, right? So we're going to remove that, and also that sets it up to be mapped by did I write Q here? This should not be Q. This should be, well, we know that Q restricted to alpha. Yeah, so I guess that's a better way to explain it. So Q restricted to alpha will just be phi alpha, right? So this is just phi alpha. So then we get that this will map to the codomain of phi alpha. So we define R as the restrict. So what does it mean to like restrict it, right? So like let's see what that means. So we define R as P G alpha beta V. Well, we have to take that at V. Remember, this is over the whole of U alpha intersect U beta, and then when we take it at P, as we discussed earlier, this gives us a single linear map. So that's clarify that. So yeah, that is the way that R restricts our function. It just removes beta and then replaces it with the linear map that takes V to alpha, to the fiber over alpha. So if we take if we look at this, right, this function is actually continuous, and it's because the first thing that it does is it takes P to P, which is the identity function, and the second thing that it does is that it takes V to G alpha beta of P. G alpha beta of P is by supposition a continuous function, so this is continuous as well. The Cartesian product of two continuous functions is a continuous function, so therefore R is a continuous function. This is going to become really useful in a moment, where if we think about, so we want Q inverse of B tilde alpha beta restricted to B tilde alpha beta after of phi alpha of W, right? This is what we're after. This is that intersection that we were going for between these two. And if we show that this intersection is open, then we've shown that all of the preimage of W is open. So the preimage of W in terms of phi alpha inverse is open. So what does this equal to? Well, this is equal to let's look at it over here. So this is phi alpha. Let's substitute phi alpha after R after phi alpha of W, and this is inverted, right? This is the, let me color code that. So that is this map, right? So then if we take that, then inverting it, the way you invert a map is like this, phi alpha inverse. Oh, but that's really neat. The phi alpha inverse and the phi alpha becomes the identity map, and the identity map on W returns W, so that's R inverse of W. Oh, that's very interesting. R inverse of W is the same thing as the intersection that we want to look at. But if that's the case, but we know that R is a continuous function, which tells us exactly that if W is open, then R inverse of W is open. But that's exactly what we want, because we've just shown through all of our arguments that R inverse of W being open is the same thing as phi alpha of W being open. And phi alpha of W being open means, because W is always an open function, or sorry, an open set, that means that phi alpha of W always being open means that phi alpha inverse is continuous. And there we go. We've proven it. So let me recap what we just did. We said that this little subproof. We first wanted to prove that phi alpha inverse is continuous. We then showed that phi alpha of W must then be open. We then showed that Q inverse of after phi alpha of W is open in T is equivalent to this statement. And then we showed that this implies that R inverse. So we then said that, okay, well, think of this U beta cross F cross beta for all beta. My squigglies are becoming unintelligible. A is an open cover. And under the subspace topology, we said that this intersection. Let me write that in the same way I've been writing it the previous times. We said that this intersection, we only need to check that this intersection is open, right? Because of the subspace topology. On T, right? Because we said that this is open, so then this intersection being open, we can take the union of all of those intersections, and then we'd get an open set, because of the arbitrary union of open sets is an open set. And so then we said that, well, this is contained in U alpha intersection U beta cross F cross beta. One thing I forgot to mention is that this is open because finite intersection of open sets is open, so this is open. So we know that it's contained, this intersection will be contained in here, but then we said that, okay, well, restrict Q inverse to this set, Q inverse B tilde alpha beta. That restricts us to this set, but then this is equal to phi alpha after R, where R is our restriction function, but then R is continuous. We showed that R is continuous, and we also showed that R inverse of W is equivalent, is equal to Q inverse of phi alpha of W, which is what we wanted to show was open, right? But if this is continuous, then this is open, which means that this is open, which means that phi alpha of W is open, which implies our last idea, which is that which implies our result, which we wanted, which is that phi alpha inverse is continuous. So now we're in the home stretch. All we need to do is to define G alpha beta. But in order to do that, we first need to understand something. So let's first, and we need to define this function that I said we were going to define, phi alpha p. We are going to define that as phi alpha of of V is going to be definitionally phi alpha of PV. That's the way we're going to define it. So we're going to restrict it to the point P. So we're now looking at a single fiber, and so then because remember, the transition functions are for transitioning between fibers as represented in different local charts. So we have the fiber, you can think of it as going from like the fiber in alpha to the fiber in beta, and we can also put a little p there so that we know to signify that it's for the point P. So that's what our transition function G alpha beta is going to do. And so we have this similar idea here where here's the vector bundle. Let's say that that's E. And we have a similar idea to the coordinate charts where phi alpha p actually, well, it moves us in the opposite direction. Phi alpha p starts in the vector space and moves up to the vector bundle. So we have a similar one here, phi beta p, where this is f beta p, and this is f alpha p. These are the same space represented in two different coordinates, and we want to talk about this movement here. So this is g alpha beta of p. So yeah, so this is what we're after here, and the way we're going to get to it is we're going to say that or actually I think we're going to do, okay, let me see. Let me look at the notes and let me keep this straight, because this is a very cumbersome part. So let's say that P is an element of U alpha intersection U beta, so that we have access to both those coordinate charts. And so then we would like to say that phi alpha P inverse after phi beta P. Right, so we're going first this way, and then we're going against the grain here. So that means that we're going this way, right? Yeah, so that's basically what I wanted to keep straight. So let's say that that's acting on V, that to give you V prime. But then if we take, if we multiply both sides by phi alpha P, then we get phi beta P of V is equal to phi alpha P of V prime. Moving on to the next page. So let's deconstruct phi alpha P and phi beta P in terms of their definitions in terms of Q. So we get this PV beta. Let me see if I've gotten that right. Oh, right. This is going to be V prime and is equal to Q of P. Oh, this is alpha. I think I have written it out. I wrote it in the opposite way in the notes. So I flipped the equation in the notes. That's what. So PV beta, right? So because we already know we're working on a single point P, a single fiber, right? So then, but remember that we didn't make this distinction formally, but I want to remind people that what it really means for 2 points on our vector bundle to be equivalent is for their deduplications to be the same. So Q is the function that deduplicates things. So if the deduplication of these 2 points is the same point, then they're actually equivalent to each other. And the clue is that we have P on both sides. So then what this means is that P V prime alpha is related to PV beta. So then if this is true, that P is equal to P, well, that's true by definition, but V prime is equal to G alpha beta of P into V, right? But notice what that means. What we started with the thing on the last page, V prime is equal to phi alpha P inverse after phi beta P of V, right? Which means that this, let me highlight that in a different color, this must be equal to this, right? Given that we had all of these implications, these are equal. So there we go. And this is well defined because all of these functions are continuous. Phi alpha P inverse after phi beta P. Now, I'm not sure that I kept the alphas and the betas straight in this definition, and especially with relation to the convention in the vector bundle that we did last time. So you can like check and like make sure that the alphas and the betas are in the same places. But you know, like if it's wrong, then just flip them where they're wrong. The proof will still work. So okay, we're not going to worry too much about that because it's mostly about the principle here. And so a V is equal to this, right? So that's our definition. That means this is what is telling us that G alpha beta are indeed transition maps. We didn't know that they were transition maps before, but these are transition maps. So there we go. We've got everything now. We've got E, we already had M, and we have the bundled projection map pi. We had the fiber F, that's how we constructed it. And now we have the transition maps, which are well defined. G alpha beta. And because we showed this, we just took two arbitrary indices, right? We took an arbitrary index alpha and we took an arbitrary index beta. So we've proven that this exists for any pair alpha beta from this index set. So there we go. This means that there exists a vector bundle on M. So we've gone long enough for today. This was a very long proof, but hopefully, I don't know if I'm going to do a long proof like this next time. Let's conclude this part, and I'm going to continue talking about tensor bundles in the next part. Let's conclude this part with a little summary of what we did. Firstly, we proved that subject to some conditions, M must have a vector bundle. Those conditions were essentially that G alpha beta is a smooth map and that G alpha is equal to the identity, and that G alpha beta after G, there's some P's here that are missing. P, beta, gamma, P is equal to G, gamma, sorry, alpha gamma of P. So if these are true, these are the most important conditions. If these are true, then smooth implies continuous, by the way. Then we get a vector bundle. That's basically what we tried to prove. This was a theorem. And in doing so, we had some substeps. What we did was, substep number 1 was we constructed E. We then constructed pi. We then constructed phi alpha p, which led us to and we showed that within which, like, we showed that phi alpha and is homeomorphism, right? Because we showed that it's is a homeomorphism. Because we showed that it was continuous with continuous inverse. What's happening? Continuous with continuous inverse. And so then we use that to define these transition maps G alpha beta. And so we concluded that there always exists a vector bundle. Now, one thing that I forgot to mention is that this is a note. I was going to mention this before the summary, but let's do it now. Note, this vector bundle is unique. Vector bundle is unique. The proof is that I talked about in Steenrod talks about this uniqueness. There's a paragraph after this part that we covered last about why this vector bundle is unique. It requires some of the results that previous results in Steenrod's book. So if you're curious about why this vector bundle is unique, we haven't proved it, and if we tried to prove it, this would be even longer. So you can look at page 12 of Steenrod. It's that same book that I referred to earlier in this part. Okay, so that's it for this part. Next part, we will talk about tensor spaces and tensor bundles. So next time, tensor bundles. I mean, that's the main attraction of the show. Tensor bundles. That will be part 3 of lecture 4. Okay. All right then. See you. Goodbye, everyone. Hope to see you next time in part 3 of lecture 4.